Sounds good. Okay, so the task of a style transfer is that given a sentence, right? So we know the sentiments of the sentence, and we want to transfer a negative sentiment to a positive sentiment. So, for example, here we have a sentence that has a bad, negative attitude, which says, "The service is terrible," and here we want to transfer this sentence to really positive ones. So, for example, we can transfer this sentence from like something really is terrible to something that is okay, and then to something that is excellent. And here in our approach, we are going to use a latent variable model to model um, this task. So, for example, we can learn a latent variable that is associated with this sentiment of this sentence, and then we can change this latent variable in such a way that we can change the sentiments, a really negative sentiment to a really positive sentiment. So the approach we're going to use today is called the disentanglement latent variable model here. So the problem of disentanglement it says that there are assumed that in the data generating process, there are k different factors that generate this our data set. So for example, in the image data set, right? So for human faces, there are factors like your age, your emotions, and your hair color, the background color, and the angle of your face. So those things are the ground truth factors that generates these face images. And the assumption of these entanglements assumes that these k factors they separate these data sets into k different parts. And disentangled factors means that if I change one factor, they will leave other parts of my data unchanged. So for example, if I only change the factors that associate with the angle of the face, that shouldn't change the hair color of the face. Okay, so one major problem in many recent studies in this line of research is that they often assume these k factors they are statistically independent, which shouldn't be the case, right? For example, if we think about the case example where I usually give to people, so for example, let's take a factor about hair color and your age. Then if these two factors they are disentangled, then if I change the hair color factor, they shouldn't change the age of this face, right? But the factor of age and hair color, they are definitely not statistically independent because a person with an older person is more likely that he or she will have more white hair. So these factors, they are not independent in the sense of a statistic. Okay, so our goal here is how we can actually achieve this second definition of disentanglement while allowing this statistical, uh, while allowing these factors to be dependent. Okay, so the first approach we tried in June and July, which actually already failed, is that we'll try something called the spectral disentanglement. So basically, um, it's called a spectral disentanglement because we are making use of singular vectors of some matrix. So here, our approach is that we first find the Jacobian matrix of our generator GZ, and um, and then we are going to find the k most significant singular vectors of this Jacobian matrix. And then there's a paper saying that these different singular vectors, which are already orthogonal in the latent space, they consist of these disentangled factors. So the approach is basically modify the latent variable z by adding these singular vectors. And then for images, actually, this one is this example comes from the spectral disentanglement for image data set. So basically, each row is an independent example, and for each column, they're going to modify this latent variable by adding the most singular vector. And then as you can see that there are these singular vectors, they form a disentangled set of factors. For example, the first singular vectors it corresponding to the factors about background color, right? So it changes something. The background is black, but here it is white, and here you change the color of the color of the faces. Yeah, but then the problem is our approach failed for sentences. So for example, we have some initial results here. So the wine was very average and the food was even less, and we can change this sentence by modifying a singular vector to our latent variable z, and then you change some words like average to nice, but it cannot change all the sentiment words to positive ones. For example, here was even less was still it still was even less. So in the end, we didn't try this approach anymore, but Steve is trying this one, so we still hope that we can modify this approach and get some better results. So here, our new approach is called causal disentanglement. So first, to introduce a causal disentanglement, we have to introduce the notion of causal inference in deep learning. So what is causal inference? So to understand causal inference, it's better to give you an example, right? So here we have an example about kidney stones. So kidney stone is a disease about kidney. Is something that when you don't drink enough amount of water, then the foods they get saturated in your kidneys, and then gradually they form the stones, right? So here we have a causal model where T is the treatment and X is the size of a stone, and Y here is the recovery time for a patient. So the arrow line here, it means the causal directions. For example, the treatment that you give to a patient should fast the recovery time. And the size of a stone should affect not only the recovery time, but also the treatment. For example, if you are unfortunate, if you're fortunate patients that your kidney stones happen to be really small, then the treatment that the doctors will assign you is usually you drink more water and do more exercise, and then gradually the stones will get washed out automatically. But if you're unfortunate and the stones are really large in your kidney, then there are treatment codes like I think they are using a technique called sound wave, where they can actually crush the stones using sound waves into smaller pieces, and then you can drink more water and do more exercise, and the stone will get washed out automatically. And then here, the example that I want to show here is that in causal inference, there's actually a huge difference between conditional distribution and the intervention distribution. So basically, if here A is let's say A is that we are using the sound wave to crash the stones, right? So the probability that the recovery time, given that we are using the sound wave to crash the stone, is not equal to the probability of the recovery time that I'm going to assign that this phenomenon is crashing the stone. So initially, when you look at this, you will say, hey, wait a minute, these two distributions, they are the same, right? So, but actually, they are not the same distribution. So, for example, if I say that, so for example, if I'm a doctor and I'm going to say, sorry, I'm going to use a sound wave to crash your stone, then it actually implies that you are a hard case. It actually implies that the recovery time should be longer, right? But let's say if your stone is pretty small, and then what's the probability of using the sound wave to catch the stone, and what's the probability of the recovery time without using the sound waves? So here, if you use the sound wave, then probability then the recovery time should be much shorter than without using the sound wave, right? But if you use the conditional distribution here, and then we assume that we are using the sound wave to crash the stone, then it automatically implies that you are hard case. So it may implies that the recovery time should be longer. which shouldn't be the case in the reality. So that's why we should make a huge difference between these two distributions. Any question about this, the difference? Okay, so here, once we understand the difference, the problem is how we can actually estimate this informational distribution rather than this conditional distributions. So in deep learning, this conditional distribution is very easy to model because we can actually model this as some parameterized neural networks. But this one is harder to model because if you think about this conditional distribution, they're actually they're actually a reflection about the observational data, right? So, but here is something that is outside of your data set. Is something that is everything in the reality, even including those data sets you didn't observe. For example, the case where you actually have a small kidney stones, but we are still using the sound waves, right? But in the data sets, usually doctor won't suggest to you to use sound waves to catch a stone when you have a small kidney stone. So that is something not in our data sets. Okay, so to estimate this one without having access to all the data in real life, we can actually do this. So basically, when I intervene this variable t here, for example, I fix this to sound waves to crush those stones, then since this latent variable it originally is influenced by the size of your stone, right? And here is fixed. We are going to delete the causal direction from x to t because t is no longer depending on x anymore. And here we are going to marginalize this variable x out because y is still depending on x. And here, this distribution, it should be y given that x, and given that we are going to intervene this t. However, this information distribution will not change the conditional distribution of y given x and t. Why? Because once we intervene t, right, t will no longer be depending on x, and we will delete the causal direction from x to t. However, this will not influence the causal directions of x and t to y, right? So y is still dependent on t and x. So the interventional distribution of y given x, and that t is fixed as some constant, is still the conditional distributions of py, given that t is using some equation stone and x. So here we can just use this condition distribution, and we marginalize this x out.
Why you times px in the integration?
Because in this case will be p by x, and then you integrate x will be x will be marginalized. Yeah. Okay, so we're going to use this model to for our state transfer. So here I actually propose this causal general model to our sentence generation. So for example, here x is the original sentence. Is here is the cause, and the z1 and z2 are the latent variables. So here z1 is the latent variable that associates with the sentiment of the sentence, and the z2 is a latent variable that is something that is everything other than the sentiment of sentence. And then here the original sentence, they are the cause of these two latent variables. And then so basically the first two arrows here, they are the encoders, right? We can get these two latent variable by encoding the x. And then the second two arrows, they are the decoders. And here the second causal graph here, it says that z1 and z2, they are the causes. And then the effects are the reconstructed sentence x prime here. So Z1, Z2, they are the latent variable that actually have some causal affection on the reconstructed sentence. And then this Y and G are the ground truth factors. So Y here is our sentiment label of each sentence which are given in the training, and the G is the latent. G is the ground truth factor that corresponding to the content of sentence. So basically, it's everything other than the sentiment. And then here, to actually make this Z1 and Z2 to be disentangled. So for example, when I change this Z2, it shouldn't change Y, the sentiment label, and when I change the sentiment latent variable Z1, you shouldn't change the content factor of this sentence X. So the approach is that we first estimate the distribution of EG once we fix the content latent variable. And then we are going to estimate the second distribution, which is still we are going to fix the content latent variable, but we are going to change the sentiment latent variable. So basically, these two are entirely two different distributions. So if our latent variable Z1 and Z2 they are disentangled, then these two distributions they should be the same. Do you see why? Yeah, because we are arguing that this when we intervene this Z1, given that Z2 are fixed is fixed, G shouldn't change. So basically, these two distributions they should be the same. And here we're going to use some metric called Vasarsen distance, and during training we are going to minimize this distance between these two distributions. So I tried this approach for a very simple data set, which is called MNIST, right? So everybody knows that. And then here, basically doing training, I'm going to make Z2 to be some, so doing training, I think Z1 is the digit class. So, and Z2 is everything other than the digit class. And then during training, I make this Z2 to be a one hot vector, which are encoded from the label that is already given during the training. And then after training, so this model is actually VE. So after training this VE model, when I intervene this Z1, you can actually see that the class digits, they are changing. Because because this D1 is actually a one hot vector that is gathered by encoding the labels. Yeah.
So I have a question that will probably be the same question for language is, so I get Y, right? I get how you get the label. What is the representation of G?
So for this one, originally the model should be Y and G, they should be the upper side.
The what?
Y and G, they should be the upper side because they are actually ground truth factors.
Right. So Y is the actual label, right?
Because
and then G is some. How do you take away the two-ness of a two?
So here is Y, right? So if we make Y and G on the upper side, then given this this estimation, we have to estimate the distribution of fixing one of Y and G to be constant, and then intervene Y and G. But here we only have access to Y, which is the sentiment label. But G is
you don't observe G. Okay.
Right. But here, once G is the cause, the effects of a cause of a Z1, Z2, and X point, then actually I can just use some relaxed approximation of G.
Okay.
For example, I can use a sentence event imported.
My point being, your observed data is X and Y, not G.
Yeah, exactly.
And that's going to be true for language as well.
Yeah, right. And the same for MNIST, right? So Y is already observed, and the G is something that is it is the let's just say it's some kind of a style. For example, different columns, the digits they have different style, right? And the different rows, they have different digit class because for different rows, I'm going to fix. I'm sorry, they should be C2 and they should be 1. that should be short. Okay, so here, as you can see, if I introduce this about sustained distance between these two distributions, where we actually fix one of the latent variable and then intervene others, the other ones, then when I change the latent variable that corresponds to the one hot vector, which is gathered from the class digits, then you can see that this latent variable is no longer corresponding to the class digit anymore. And the issues for this is that when we actually apply this to sentences, it is actually very hard because when we estimate this distribution, we have to fix one of the latent variable to be constant, and then we are going to intervene the other ones. So basically, we are going to change the other latent variable. But if they are continuous as the sentence variation of the encoder, then we actually don't know how to choose the value of this continuous latent variable, right? So the approach that I made up for this week is that I'm going to use categorical distribution for one of the latent variable, right? So for example, here Z1 is the latent variable that corresponding to the style label or the sentiment label, and then I'm going to make it to be a categorical latent variable. So basically, I'm going to sample Z1 from a Gumbel softmax, and the Gumbel softmax is a continuous relaxation of a categorical distribution. So it is continuous and it is differentiable, so we can backpropagate the gradients. And here y is basically the individual dimension of z, and then this pi is actually the probability of each sentiment label. And then once I get this, I can actually estimate the distribution such that I'm going to fix the other latent variable to be constant. And here I can just sample z1 from 0 and 1. And this one is easier compared to the continuous approach because I know that the value of Z1, the values that Z1 can take, they are finite because it is discrete. And I guess the future direction will be finish the training of this one and then see what the results be like. Yeah, I know you have other questions. Thank you.
So you said you will change Z1 or Z2. So how do you do by changing them? You add some small number to Z1?
For example, here Z1 is actually a continuous version of one hot vector, right? So if you use the Gumbel softmax, then it would never be a one hot vector. But it will be something that is close to one hot vector. But when you do intervention, you can just make it to be one hot vector. Like, for example, here, if our sentiment label are, we have two sentiment label, negative and positive, then we actually can sample Z1 from 1, 0, and then 1 is 0 and 1, right? And then when we do fine-grained control, actually, we can do something like 0, 1, and then 0.9, and then 0.2, 0.8, which should be something that is not very negative. So for example, 0.5 and 0.5 could be something that is neutral, and then 1 and 0 could be something that is positive, and 0 and 1 could be something that is negative. Yeah.
And in the training data, the sentence will be this part, a part of the sentence is annotated by positive or negative or neutral label. So that's what the training data look like.
Yeah, the training data we have the sentiment label.
Sentiment.
Yeah.
For the whole sentence or for just
for the whole sentence. Yeah.
Maybe a very naive question, but what is the advantage of this approach over existing style transfer or sentiment transfer approaches?
So the advantage is that for the current ones, I guess there are two different advantages. So the first one lies in the direction of disentanglement. So in the usual disentanglement approach, people usually assume that this latent variable they should be independent in the statistical sense. And here, if we use this culture inference, we can actually allow them to achieve the true disentanglement while actually encouraging this statistical dependence between these latent variables. And then the advantage for style transfer, I guess the first advantage is actually here when the training has only two sentiment label, which is negative and positive, then you cannot actually do fine-grained control generations because you want to, for example, you want to generate something that is selectively negative, and then you want to generate something that is neutral, but these sentiments label, they are not given in the training data sets. However, you can actually say that I'm going to make the Kadu distribution to be higher dimensions, right? So for example, rather than make this dimension of a pi to be 2-dimensional, I can make it to be 5-dimensional and even 10-dimensionals. And actually, people try this with MNIST, right? So for example, they have this model here. So in MNIST, they make C1 to be a category distributions. And then basically C1 is the probability. So C1 is sampled from this gamma of max, and this pi I is the probability of each digit class. And then when they after they train this VE model, and then they calculate the accuracy of this pi I, they actually observe the accuracy is pretty high, which is 90%. And then that is really amazing if you consider it, because this is this version of encoded. It is entirely unsupervised approach. So you don't have access to a label when you do the training. But still, this probability of pi, you can recover the true probability of each digit class. So for example, when you want to do fine-grained generation, and when you don't have some classes that is in your training data set, you can just make it to be higher dimensional. Yeah. Thank you.
All right, let's give our speakers another round of applause.
Appreciate your socks.
So nice seeing you.